In this video, we are going to estimate the population mean using confidence intervals. Given a population, if we want to study one characteristic which is quantitative, this characteristic must have a mean and a standard deviation. However, in most of the cases, to compute the mean of the population, it is too difficult or impossible. For that reason, we select from the population a representative sample, and in this sample we compute the sample's mean. This sample's mean receives the name of point estimate, and we are going to use this sample's mean to estimate the population parameter. When we select a sample, we have two possibilities. The sample is bigger than 30, the sample size is bigger than 30, or the sample size is smaller than 30, which is a small sample. In a previous chapter, we studied that the distribution of all samples mean follow a normal distribution when my sample size is bigger than 30. The population could have any distribution like this, very ugly, and with mean mu and standard deviation sigma. However, if my sample size is bigger than 30, the distribution of all samples mean follow a normal distribution, and the center of the distribution will be the true parameter, that is the mean of all samples mean, and the standard deviation of all samples mean is the standard deviation of the population divided by square root of n. If we know the standard deviation of the population by previous studies, we can transform this normal distribution in the standard normal distribution, z-score. Remember, in this distribution, we have all samples of the same size represented by points, but we organize all of the samples according to the sample's mean obtained on each of them. For example, for this sample specifically, the sample's mean is located in this number line here. Then, if we want to obtain the z-score of this specific sample, we do this operation, the sample's mean minus the true parameter divided by the standard deviation of the population divided by a square root of n. Then that is the distance of this value respect to the center given in this standard deviation. If we obtain the z-score of all samples mean, we can obtain that distribution, and we observe that here all samples located here, the distance from the center is 0 and are all of the samples, and this is the mean of the standard normal distribution, and the standard deviation of the standard normal distribution is equal to 1. Remember, within 3 standard deviation to the right and 3 standard deviation to the left, between negative 3 z-score and positive 3 z-score, we have 99.7% of all samples. However, the standard deviation is the deviation respect to the mean. If we don't know the mean, it's very strange that we know the standard deviation. Then the most common case is when we don't know the standard deviation of the population. Then, if we don't know the standard deviation of the population, which is common, instead compute the z-score, we compute the t-value. What is the t-value? It's very similar to the z-score. The t-value is computed using the same formula for the z-score, but instead the standard deviation of the population, we use the standard deviation of the corresponding sample. If we compute the t-value for all possible samples of the same size, then we are going to obtain the t-distribution. If we compute the t-value for all samples also located here in this pile, all of these samples have a sample means equal to the parameter. If we compute the t-score, all these samples will be stuck here. then the t-value will be 0. And that is the mean of all t-value. And the standard deviation of the t-distribution is bigger than 1. It means that this distribution is more spread than the z-distribution, the normal distribution. It means that this tail is thicker, both tails are thicker than the tail of the normal distribution, are thicker and longer. It means that the t-value are more spread. In this standard normal distribution, all values, 99.7% of all values are between -3 and +3 z-score. And 95% of all z-score are between -2 and +2 z-score. However, in the t-distribution, when the sample size is equal to, for example, then 95% of all values are between -12.7 and +12.7. When my sample size is 3, 95% of all values, all t-values will be between -4.3 and +4.3. If we increase my sample size until 30, then 95% of all t-value will be between -2.04 and +2.04. Those values are very close to the values in the standard normal distribution. 95% will be within -2 and +2 z-score. This is the table for all t-distribution. In this column, we have the degree of freedom. The degree of freedom is equal to the sample size minus 1 always. For example, if my sample size is 2, the degree of freedom is equal 1. And in this row, we have the area on the right tail. For example, if this right tail were 2.5%, we can write this percentage like 0.025. This area on the tail is located in this row, which is exactly here. And the t-value which correspond to this area is 12.7 when my sample size is 2 and the degree of freedom is 1. When my sample size is 3, the degree of freedom is 2. Then the corresponding t-value for this tail 2.5 is 4.3. And if we increase the sample size until the degree of freedom is, for example, 30, the sample size is 31, then the corresponding t for 0.25 will be 2.04, as you can observe here. In this table, each row represents a different t-distribution depending on my sample size. In the next table, we have t-distribution when the degree of freedom are bigger than 30. You can observe that this last row is the summary of the normal distribution. We can find in the last row some value from the two tables of the normal distribution. For example, for a 95% confidence level in a normal distribution, this tail should be 2.5%. If we write this percentage in decimal, it's 0.025%. And we have studied before that this critical value in normal distribution is approximately 2 standard deviation, but exactly is 1.96. That is the corresponding critical value in the normal distribution, which is the value that appears here. And you see, for 2.05, that is the corresponding z-score. Then, when my sample size is bigger than 30 or equal to 30, then we can obtain the confidence interval for the true mean of the population in this way. Is my point estimate x bar from my sample plus or minus the maximum error. But remember, the maximum error will depend on the sample size and also the confidence level. If the confidence level is 95% or 90%, whatever, we need to find this critical value. Then the maximum error will be this distance. Then this critical value could be obtained here in the normal distribution. When sigma is known, then the maximum error will be given by z alpha half, that is this critical value, times this standard deviation. That is the maximum error. And when sigma is unknown, then we need to use the t-student distribution. Then my maximum error will be computed by t alpha half. But instead, the standard deviation of the population, we use the standard deviation of my sample. And this critical value will be obtained in the t-student distribution using the same procedure. If the confidence interval, for example, is 90%, then this area on the right tail should be 5%. And we need to find in the table 0.05, and according to the sample size, we can obtain this critical value for t. Remember also that in some problem, when n is bigger than 30, the standard deviation of the population could be approached for the standard deviation of the sample. But basically, we are going to use, in most of the cases, this formula that is more accurate to t distribution when we don't know the standard deviation that is the normal case. When my sample size is smaller than 30, then we need an additional condition. My sample is small, but my population should be normally distributed. Individual value must have this distribution normal. The mean, the center is mu, and the standard deviation will be sigma. If we want to estimate the population mean using a small sample, smaller than 30, and the population is normal, then we have the same situation. The distribution of all samples mean follow a normal distribution because the population is normal. And if sigma is known, we can use the standard normal distribution. We can use z-score, but this case is rare. It's not common. We don't know the standard deviation of the population when we don't know the mean of the population. And if the standard deviation of the population is unknown, then we have to use the t distribution. If we use the t distribution, we are going to use this formula to construct our confidence interval. But remember, we can approach the standard deviation of the population using the standard deviation of the sample when my sample size is bigger than 30. Only when my sample is smaller than 30, we need to use the standard deviation of my sample and the t distribution. Basically, we are going to use the same procedure when my sample is smaller than 30, but we need an additional condition that the population should be normal. The majority of the problem in this chapter, sigma is unknown, then we have to use always, either when it's bigger than 30 or smaller than 30, the t distribution. But when my sample size is smaller than 30, we need to verify that the population is normally distributed. We can verify that the population is normally when we input the sample in a stacked crunch, and in a stacked crunch we obtain the PP plot, and in the PP plot we input the data. If we have, for example, 17 values, then we have 17 points that must be close to this theoretical line and inside these dot lines. If all points are inside this two dot line and close to this theoretical, we can assure that the population is normally distributed. Also, we can use box plot, and in the box plot, remember, we use the first quartile, the second quartile, and the third quartile, and these are the whisker. If we have no outliers, then the distribution could be normal. But if we have outlier like this, then the population is not normal. Then this graph, the graph of the box plot, that also you can obtain the box plot from StatCrunch, must not have outliers. After you verify that the population is normal using either of these two procedures, then you can use this mathematical model, the t-distribution, and that are the most important concepts in this chapter.